Let's get this show on the road. Okay, so today we continue our discussion of differential equations and engineering analysis, and I want to kind of frame what we talked about last time, where we ended things. Certainly not where we'll end things today, but kind of it's an ongoing development of trying to come up with these equations that describe different physical processes. And I presented you with a few different systems of potential relevance characterizing different physical phenomena, such as mass transport, maybe looking at some kind of bucket filled with water that might have sort of some, I don't know, permeable exterior boundary through which some fluid might be able to flow in or out, and which might also have some kind of local mass generating source term interior to the volume of this kind of bucket of water. That was kind of our mass conservation equations being postulated in the format of this sort of system-specific examination of how does mass remain conserved in a universal sense if we're only really considering maybe some kind of local system of interest which can potentially still interact with its surroundings. And we came up with some set of equations concerning what's the time rate of mass contained within this kind of small bucket of practical interest. And we noted that the time rate of change of the mass contained within this kind of small system can be characterized through, as I mentioned, any potential mass source terms or local generating spontaneous creation of mass that happens inside of this kind of volume has to be accounted for by any maybe source terms which generate some kind of rate of mass per unit of volume. And the total, contributions from these source terms can be integrated over this whole kind of specific volume of interest to come up with that contribution to the total local change in mass of the system. And in addition to that, we also have the potential for mass to flow out of the volume or into the volume through these so-called flux terms. And a flux is really nothing more than basically, an exchange of some particular quantity of interest, in this case, mass. And more specifically, it's the rate of exchange of that quantity per unit of surface area along the boundary of this particular system that we're looking at. So in the case of the mass flux, it's a time rate of mass per unit of a surface area that might be leaving or coming into this domain. And we can basically integrate over this entire external boundary that flux of mass to measure how much mass is leaving, how much mass is coming in, and in an integral sense, what's the net flow of mass that, time rate of flow of mass that might be entering or leaving that system. And that too contributes to the total change in the system mass. So both of those two terms, characterized by basically these two integral expressions, we came up with some derived expressions of these different flux terms in terms of some flux vector, which I arranged as basically being some vector consisting of individual components of the flux that might differ depending on which oriented surface of this particular system am I looking at. So if I'm looking at some kind of x-directed face, this right-hand face of this block, then I might have some mass flux J sub x that's kind of pointing this way. On this top face, I might have a vertical flux J sub y pointing in the vertical direction on this y-directed face. And the values that I get for the flux on these different faces depends on the orientation of these different faces. And we derive this kind of relationship between what's the particular flux acting across a particular surface with some corresponding surface normal n. I was able to derive that any kind of particular flux across a given surface is related to the total flux vector, the vector containing all these different components, J sub x, J sub y, maybe J sub z if it's in 3 dimensions. And the dot product between the normal vector of a given surface with the total flux vector gives me the effective flux across that particular directed surface. And that was kind of a convenience just to be able to more compactly consolidate all these different terms and represent things in terms of this kind of vector of different flux components in the context of mechanics. Switching gears and noticing that there's a lot of analogs between statements of mass conservation and statements of momentum conservation, it turned out that similar concepts applied. If we were looking at what's the total change in momentum of this system, which might consist of some kind of block that's being acted on by a bunch of different external forces along the exterior boundary of this block, as well as maybe any kind of local body force terms or forces that act at a distance, but which act over the entire interior volume of this cube. In that case, we can kind of sum up all the different forces that act on this cube, any interior body forces integrated over the volume, any exterior tractions, as I kind of called them, tractions being basically a force per unit of surface area. I can integrate the tractions over the boundary to come up with what's the net external force acting on the boundary. And through a similar kind of twist or manipulation, I was actually able to come up with some relationship between a new quantity, which I called the stress tensor, which was really just an organized array consisting of all the different components of the exterior tractions that act on all different faces of this particular cube. And I can arrange them in this way where I might have, let's say, an x component of traction, or basically a force per unit of area that acts in the x direction, but which acts on some x-directed face. And I might have called that x sub xx, or rather sigma sub xx. And I could go through and basically define all these different components of stress. I could organize them into the format of a 3x3 array if I'm looking at a problem in 3 dimensions. And another word for a 3x3 array is just a rank 2 tensor. Hence, we came up with this object, the stress tensor, which, as it so happens, if I wanted to know what are the particular components of traction or force per unit of area acting on any one of these different faces, I could come up with what are those components by basically taking this stress tensor object and taking sort of a matrix vector multiplication of the stress tensor with the corresponding surface normal vector to come up with those particular traction components. Using that, I can kind of come up with this new expression that basically reformulates things in terms of not just an integral of traction, but the integral of this stress tensor thing with a dot product against the normal vector, which might vary depending on the surface you're looking at. Okay, so heat flux, very similar kind of concepts, especially in analog to the whole concept of mass transport. If you like to think of it, heat being transported through a body is somewhat analogous to mass being transported across different interfaces. So I won't kind of dwell on that. But the main thing I want to conclude here is that basically we have these different expressions. We have time rate of some quantity, enclosed within this particular system volume. I have some contribution of some interior source term being integrated over the interior volume. And I have some kind of quantity that's measuring what's happening on the boundary, basically, to exchange either mass or momentum, depending on some external flux terms or forces or tractions, basically. But the problem is I don't actually like this. I don't like the fact that I have 2 different types of integrals here, an integral over the interior volume and an integral over the boundary. What I would really like is to actually convert one of these integrals, let's say this one, into an equivalent integral over the volume. And you'll see why we do this. But the ultimate goal is to try to come up with some expression that's completely expressible in terms of some integral over the volume of some kind of set of equations, including a source term and maybe some other stuff. And in order to do that, it so happens that by introducing these notions of some kind of flux vector or a stress tensor with a dot product involving some normal vector integrated over some exterior closed surface, it so happens that that is actually a particularly convenient quantity to have manipulated these expressions into. And the reason has to do with something called the divergence theorem. This is something that you maybe have been exposed to, at least in maybe a multivariate calculus course, but the analog to the divergence theorem in one dimension is just the fundamental theorem of calculus, which is probably something that you well remember. The idea is this: the fundamental theorem of calculus states in one dimension that the integral of some function f, or rather the integral of some derivative of a function f, so the integral of df dx with respect to x basically gives me back the function itself, right? It's kind of like if I take the integral of the derivative of a function, I just get back that same function again. And if I have a definite integral, which has specific limits of integration, let's say between a value of x ranging from x equals a to x equals b, then in order to evaluate this kind of integral of the derivative of this thing between these two limits, all I have to do is take f evaluated at b minus f evaluated at a. So in effect, I'm kind of equating some evaluation of this function f on the exterior boundary of this particular domain of interest between a and b to an equivalent integral expression that involves an integral over this full kind of interior domain. And that's an interesting connection. Basically, it says that I could either take sort of this interior volume-like integral of the derivative of this function, or I could just evaluate this function directly on the boundary. But if I evaluate on the boundary, it has to, respect the fact that if it's on the right boundary, I have to add a plus sign here. If it's on the left boundary, I have a minus sign here. So there's sort of a sense of, if I'm integrating, this function over the interior, I can just integrate its derivative between a and b, but that just gives me, some evaluations of f at the endpoints of this domain. Now, the analogous concept in the case of multivariate calculus is precisely this thing that I've called the divergence theorem, which is essentially the same concept. It's just generalized to accommodate transforming what was originally maybe a volume integral of the derivative, or gradient in this case, of some quantity over some interior volume. I can actually transform this expression, an integral over, let's say, the interior of this maybe particular system or volume of interest. I can transform this integral into an equivalent integral over the surface area or the boundary of this domain. And it's a little tricky how exactly you come up with this expression through some derivation, but the idea is this: the integral over the volume of this thing involving what's called the divergence of some vector field. So supposing I take this particular example of the mass kind of flux problem, the divergence of the flux vector is really nothing more than basically the entry-wise sum of the j component of flux, partial derivative with respect to x, plus the partial derivative of the j component of a flux with respect to the y component of spatial position. And sum all those different components together. That gives me the divergence. On the boundary, the equivalent integral that basically is exactly the same as taking this integral evaluation is just the thing that we actually previously developed. It's integrate over the boundary, this kind of flux vector, but take its dot product with the exterior normal vector and then integrate that thing over the full exterior boundary. So I can do either one of those two things, and they're entirely equivalent. So I can either integrate over the boundary, this flux vector dot product with the normal vector varying over the exterior boundary, or I can transform that into this equivalent volume integral involving the divergence of the flux vector itself. So that's really the critical missing component that enables us to take these integrals, what were previously a volume integral and some boundary integral. We can now consolidate that kind of disparate expression into an equivalent full, just only volume integral. So this term, the basically the dot product between the flux vector and the normal vector integrated over the exterior surface of this system can be transformed into an equivalent integral over the volume of the divergence of the flux vector. All right, very cool. Now we have everything in terms of a volume integral. In the case of this kind of summation of forces acting on this cube of interest, we can do a similar thing applying the divergence theorem to this exterior boundary integral that's integrating the exterior attraction that acts over the whole kind of boundary of this cube. And it turns out it looks kind of similar. In this case, what we get is the stress divergence, is what it's sometimes called. So rather than taking sigma, the stress tensor, dot product with n integrated over the boundary, now it becomes the divergence of the stress tensor integrated over the volume. And it's a little tricky exactly how the components of this work out. But if you wanted to write it in index notation, you can kind of think of it kind of like this. The divergence, let's say, of this particular quantity is basically that. So if I have, if I define my divergence of this kind of stress tensor, which is basically, thinking, again, it's a 2x2 or a 3x3 array. Really what I should get out of this is the divergence, basically operator, if you like, is kind of like a vector. And if I take the dot product of a vector with some matrix, I'll get back another vector. Using Einstein's summation convention, I can write out the specific components of what that resulting vector should look like. And it turns out that those components, which range from j equals 1 to 3, should be exactly these quantities. I'll show you explicitly what these components look like in a full expression later on. But just to give you a sense that really this expression, the divergence of the stress tensor, gives me back a vector, effectively. And that's important, and it should be the case, because really this body force term, or force per unit of volume acting over the interior of this domain, this is also a vector quantity. So if I'm adding these two things together, they should really be the same. This should be a vector, and this should be a vector. And indeed, they are. All right. So we've transformed everything into equivalent volume integrals involving these different quantities of interest, but there's still something that we have to deal with. And that's, well, how do we actually kind of measure this time rate of change of this conserved quantity that we're looking at? In particular, the time rate of change of mass, or the time rate of change of momentum, or time rate of change of this internal energy term, thermal energy in particular. And we can characterize some relationship between what's the total mass enclosed in this block of material, or what's the total momentum enclosed in this block of material, by basically saying, well, don't think of it in terms of these extensive properties as we previously defined them, things that depend on the size of these different systems. Define things in terms of these intensive properties, things like mass density or momentum density that involve rho, basically the mass density of this chunk of material. And if I wanted to recover what's the total mass of the system, all I have to do is just integrate the density over this volume, or integrate the momentum density over this volume to get the total momentum of that object. But here's the trick. I could certainly come back and say all these previous expressions that we developed, in particular this one that says the total change in mass of this system, at least its time rate with respect to t, is equal to this thing. And if my goal is to really transform everything into equivalent volume integrals, the challenge is now characterizing this, involving some dependence on the density. If I try to take the time rate of this thing, well, it's very tempting to say, well, I have an integral involving this kind of density term on the interior of that volume integral. And wouldn't it be nice if I could just take this, derivative with respect to time and just push it inside of the integral itself? And then basically what I should get is just the integral over the volume of the time rate of change of density interior to this thing. That would work if we can assume that how we've defined this particular system volume, if it doesn't change as a function of time, then we have nothing to worry about, and we can do exactly that. However, I want to at least allude to the fact that there are different ways in which we could actually define this system that we're looking at. And in particular, there are different ways that we can define how it changes over time. And really, there are two primary ways that we can do that. The first way that we can choose to define this, I guess you could call it system volume and how it changes over time, is to kind of consider a few different things. But before we get there, we really have to define how does, let's say, some block of material, maybe that starts out as a perfect cube or square, how does it change over time? If we're looking at material points, and if we're looking at how those different points potentially move over time. And the way that I'll go about defining these different kind of descriptors of motion is by supposing that there exists some reference configuration of this block of material existing at some reference time, which I'll just call t equals 0, time equals 0, let's say. I can consider all the different points that exist in this cube of material, and I can give them names. I can look at particular material points in this cube, let's say this corner, and I can give it a name. I can, call it something, or I can just give it a name that corresponds to its spatial coordinates. And in fact, I will call points whose coordinates are specified relative to this reference configuration of this body, capital X. So canonically, if I'm denoting things in this sort of lightish gray color or using capital letters, I really mean reference configuration coordinates describing points in this originally cubic kind of domain. Now, at some later time, maybe this particular material point moves or displaces by some kind of finite amount. And its new position, which I'll call lowercase x, certainly it will depend on how far that point has displaced. And I can measure what's the particular displacement of any given point, depending on where was it originally. So what was its initial position? And at what later time am I kind of examining its new position? So in effect, I can characterize the dependence between this particular new displaced position in the so-called current configuration or deformed configuration of this block of material by saying that deformed positions of points which had some original coordinate, capital X, will deform into this new position at some later time, t. And it'll certainly vary as a function of time. So all of this really comes to the question of how exactly do we define these different system volumes of interest? If we're trying to say, let's define some kind of fixed volume over which maybe material can come in, maybe material can leave, but my perspective is always going to remain fixed. In other words, I could choose to define my system volume, omega, as basically just like this fixed window in space. It doesn't move. It's the mass or any kind of material that comes in or out that moves. So even if I'm looking at maybe some originally cubic block of material, if that block of material maybe deforms, maybe it translates, it goes somewhere else. If I choose to define my reference configuration of my, let's say system volume, such that it remains fixed in space, effectively, I'm kind of getting around this issue of saying that really this system volume, it shouldn't change with respect to time, but the cost that kind of gives you is that basically now I'm just letting material points leave or come in almost at will. Now, this particular choice of specifying some kind of control volume, as it's sometimes referred, is consistent with a so-called Eulerian reference frame. Who's kind of maybe heard of this terminology of defining either a control volume or kind of thinking of things in terms of an Eulerian reference frame? Is this kind of a new terminology? You've heard it before? I think You don't want to repel it. Well, the good news is, Eulerian reference frames are really useful when you're trying to describe motion of fluids. Fluid mechanics really takes more of an Eulerian perspective on the universe because oftentimes fluids can move around a lot, right? And it's not really sensical to define the movement or deformation of fluids in a way that kind of attaches itself in some fictitious way to the motion of some, collection of material points. So it's usually easier, at least from the perspective of fluid mechanics, to say, well, let's just hold our perspective of some particular control volume fixed in time, and then let's allow fluid to come in, maybe fluid can leave, and that'll be kind of the choice of how we choose to define this particular system volume. That's great for fluid mechanics, but I want to remind you that this course is finite element analysis of solids and structures, which means that really this description of defining some kind of system volume in this kind of fixed spatial reference frame in an Eulerian perspective, it doesn't really work for us. We'd like to have a slightly different perspective, and that alternative perspective is obtained precisely by choosing to define our kind of system volume such that it can deform over time and move along with the deformation of some collection of fixed material points. And this particular choice of defining a system volume so that it always encloses this same collection of material points, this is called a Lagrangian reference frame. And it's much more typically applied to things like the analysis of solids that undergo some kind of reasonable, not so large deformations. So as long as, the collection of material points doesn't become too scattered and go all over the place, choosing a Lagrangian frame of reference is particularly nice. Now, the problem with Lagrangian reference frames is that, in fact, our definition for this control volume, or this kind of particular system of interest, that this volume is going to deform over time. It's going to deform along with the deformation of this collection of material points. So it doesn't remain fixed. And that really presents a problem if we want to take, let's say, the time derivative of an integral of some quantity taken over this interior volume, because the definition of that volume changes with time. How you actually convert, that time derivative of an integral over this thing becomes a little bit more complicated. However, there is a little bit of a convenience that we can exploit, and that is that we can choose to define all of these different integral quantities in one of two ways. We can choose to refer back to this kind of fictitiously or arbitrarily defined reference configuration of this collection of material points and just say, well, let's look at, maybe some quantity of interest, let's say mass density. And let's actually define mass density as specifically mass per unit of reference volume. And from that perspective, we can choose to integrate the total mass of points contained within this block by considering the integral of this reference density taken over the initial or reference configuration of this block of material. Equivalently, we could choose to integrate some density measured as mass per unit of deformed or current volume of this kind of system taken in an integral over the current volume in its deformed state. But that introduces this kind of dependence on time and time deformation of this volume. We don't really want that. So to get around that problem, we can just say, let's just integrate everything over some reference configuration or some reference volume that at least, at time t equals 0, basically remains fixed. So we can say, if I'm taking an integral over some reference volume of some fixed collection of material points, effectively, there's no time dependence of this kind of reference volume. And that's precisely what enables us to actually convert some of these integrals into something that looks like this. So if I have, let's say, the time rate of change of mass of this system, as defined previously, total mass could be defined in either one of these two ways. But if I choose to define it as an integral of a reference density integrated over reference volume, which has no dependence on time. Then if I want to take the time rate of mass, I can just take that partial derivative with respect to time and push it directly inside the integral. And that's exactly what we do in the case of Lagrangian reference frames when we're looking at solids. So we worked around this problem, but we had to be specific about how exactly we were defining this kind of reference frame of interest by isolating attention to fixed collections of material points. So in fact, if we're looking at some particular system of interest from a Lagrangian reference frame, we're always going to be looking at the same collection of material points or material particles. Even if one particle tried to leave the system system volume would deform such that it always kept all those particles enclosed. So mass is not allowed to leave or enter in the case of a Lagrangian reference frame, at least as far as how we've defined it. Now, in fact, we can take all these reworked expressions, we can come back to the table of some of those expressions we developed previously to come up with, again, a set of equations that are expressible in terms of all of them integrals over some interior volume, where that volume in this case is defined as the reference volume of this kind of block of material. So with respect to how this collection of material points was picked at some arbitrary point in time t equals 0. All right. So as long as we do that, now we have all these different expressions governing the time rate of change of mass, momentum, and energy expressed in terms of these volume integrals. Here's a volume integral involving the time rate of change of the reference density. And here's a volume integral involving, any source terms generating mass and any kind of flux terms that might be, transferring mass between the exterior, surroundings and the interior volume of this system. Similarly, here's an expression that gives us the time rate of change of the momentum density local to this kind of interior of this system and in balance with any kind of body forces that might be applied over the interior and any kind of exterior tractions that might act over the boundary of this kind of block. Now, what we can do with this is we can say, well, I haven't really been specific about which specific kind of window am I going to choose, which specific collection of material points am I going to say that this condition must hold. In other words, I haven't said anything about what this kind of particular subdomain of interest is. It's arbitrary. I could choose it to be anything. I could choose it to be, let's say, if I have some structure, I don't know, maybe it looks a bit like this. Maybe it's a cantilever beam, kind of a chunky one. Maybe it's got some external loads applied to it and some other constraints imposed on it. I can choose this system of interest to encompass, let's say, this entire cantilever beam. And I can say that, basically the net momentum change of this cantilever beam basically has to be balanced by whatever external forces are applied to this system, maybe also including reaction forces or things acting on the boundary, and maybe any kind of body forces that might be acting over the interior volume. That has to hold for this particular choice of my system, let's say. However, I could also just equally say, well, sum of forces acting on this cantilever beam, giving me equilibrium, or in the case of dynamics, the rate of change of the momentum of this system as a whole. I could impose that on the entire system, or I could just say, well, let's pick some small subset of this system and say that really over this block, here too, the equations of mass conservation and momentum conservation, all these concepts, they should be equally applicable to this small subset of this system too. There's really nothing that says that the laws of physics shouldn't hold for, this subset, but should hold for this whole thing. Equally, I could say, well, what about the subset of this subset? You could keep going down into this crazy Russian doll situation, and who knows where it ends. But the idea is this. it doesn't really matter what you choose for this particular reference domain. In fact, this condition, mass conservation, momentum conservation, energy conservation, all these principles should hold in a universal sense, which means that if I choose any possible kind of reference volume or collection of material points to begin with, that throughout the whole universe, any possible reference configuration of material points should satisfy these different conditions. If I continue to take that perspective and say, let's just shrink our perspective of this smaller and smaller and smaller, such that this reference configuration maybe could even shrink down to a singularity or a single point, then I could basically make the argument that every single infinitesimal point in the universe has to satisfy this expression. Regardless of how big this control volume is, regardless of where it is, this expression always has to be true. And because of that, I can basically say that, well, if I wanted to, I could just extract the interior integrand of these corresponding volume integrals over this arbitrarily defined, volume domain, and make the argument that the interior integrand, that expression, has to be true everywhere, at every point in the universe. And what I get out of this is effectively an equation that looks like it's just, derivative of this kind of single quantity equals this kind of quantity here. All right, well, that's fair enough. But what's deceptive about this representation is that it kind of misses a lot. It doesn't convey the idea that really this equation, it's not just a single equation. It's an equation that must hold at every single possible point in the universe. Similarly, this statement, which is basically a kind of a pointwise statement of mass conservation, the same arguments can be applied to determine pointwise statements of momentum conservation and pointwise statements of energy conservation. And what I get, again, are sets of equations that might look like, oh, this is just one equation, right? But really, it's an equation that has to hold everywhere. At every point within this structure, I have to have equilibrium, which is kind of like saying, if I were to cut up this particular cantilever into a bunch of small boxes, or Lego blocks, or Minecraft blocks, or whatever you kind of prefer, each one of these individual blocks has to be in a state of equilibrium. There's nothing that says that it shouldn't be in a state of equilibrium. But that fact basically says that for every single possible one of these blocks, I have to satisfy this equation. So it's kind of like saying this equation applies to this little chunk of material, to this chunk of material, and to basically any arbitrary chunk of material, and more specifically, to any chunk of material that might have infinitesimally small size. So really, these equations are statements of equilibrium described in a pointwise sense everywhere through this kind of cantilever beam, or everywhere in the universe, in fact. So that's a really powerful concept. It basically conveys this idea that if I have a set of governing differential equations, which are precisely what these things are, there's some partial derivatives with respect to time. There's some partial derivatives with respect to space in all of these different expressions. Effectively, they all convey the same idea, some kind of conservation of some particular quantity of interest, mass, momentum, or energy, but expressed in terms of these differential equations that have to hold in a pointwise sense everywhere. And that's really the essential idea behind governing differential equations in physics. They're intended to capture this idea that these conservation principles have to hold at every single point in some particular structure or anywhere, really. All right, now what can we do with this? Well, as I've kind of pointed out, we've derived these principles really from the perspective of saying that maybe mass can enter or leave some particular system, but so far we haven't really said anything about exactly how do we characterize, what actually controls the rate at which mass might enter or leave some system. Similarly, I've said maybe there are some external forces that act on some of these blocks, but I haven't said anything about, well, how do I actually determine what those stresses are? How do they come about? Where do they come from? What generates stresses in general, especially if I'm looking at what creates stress between maybe two nearby material points? How do I determine what's the stress or the force that might hold those 2 points together and prevent them from separating and flying off into infinity? Really, to be able to describe those things, to characterize, where exactly do I get the apparent flux or kind of mass transport, or where do I get stresses? Where do stresses come from? I really have to develop maybe some additional observational equations that relate stresses or mass flux or heat flux to some other quantity of interest. And in particular, I'd like to relate it back to the fundamental quantities that are conserved in these different expressions. In particular, what I'd like to do is come up with a way of relating, let's say, the rate of mass flux happening on the exterior boundary of some kind of block of material to something to do with the apparent density in the material, or kind of the relative density surrounding a particular point. Similarly, I might want to describe stresses in terms of something that has to do with the deformation or the motion of material points local to some chunk of material. Or in other words, strain. I want to come up with some relationship between stress and some deformation quantity, i.e. strain, that gives me a connection back to these fundamental or primary variables of interest. It so happens that, at least in this case, there are some actual really interesting direct analogs between all three of these different domains of physics, mass transport, or I guess if you like, just general kind of like a transport of any kind of concentration of some substance. Also, mechanics, as well as heat transfer, all of these different domains have an analog in trying to define some quantity that establishes what is the flux of material dependent on, something to do with the density. What is the stress in this material depending on something to do with displacement or something like that. And all these different quantities that try to relate those things to one another are sometimes generically referred to as constitutive relationships. They effectively define precisely those conditions that relate what is the flux to some variation in the local density of the material in some neighborhood surrounding a particular point of interest. In the case of mass transport, this is called Fick's law, and this governs basically diffusive transport. If there's some kind of difference in concentration of mass, let's say, that exists in some substance or a fluid or something like that, Fick's law basically says that mass that's more concentrated over here wants to move to a location maybe over here where there's less concentration. So if there's a high amount of mass density located in this position and there's less mass density over here, the tendency will be that that mass will want to transport itself in kind of a diffusive fashion into a region where there isn't as much mass. It's trying to kind of achieve this state of, diffusive equilibrium, if you like. Fourier's law, which is basically a statement of heat transport, is effectively an equivalent statement that says, some chunk of material that might have a very high temperature over here as compared to, an adjacent chunk of material that has a relatively low temperature. Fourier's law of heat conduction basically says that temperature or heat will want to propagate from this kind of region of high temperature into this region of low temperature. And effectively what that gives us in both of these different cases is that it says that if there's a gradient or if there's a relative difference in density or temperature, depending on your kind of interpretation or analog of these things, that if a gradient exists, then the direction in which mass will flow or heat will flow will depend on basically the direction of that kind of gradient. So mass and heat will always flow in the direction that basically matches with the gradient of these different quantities of interest. Hooke's law is actually somewhat similar, although the interpretation of it is a little bit different. But the idea is we can similarly define some relationship between the stress in some block of material and the corresponding strain in that material, as you're probably used to thinking of it. In a one-dimensional sense, this makes things a little bit easier to swallow. You're probably used to thinking of stress equals Young's modulus times strain. And that's kind of certainly an example of a constitutive model that characterizes linear elastic behavior, but in a one-dimensional sense. In a more general sense, we can come up with some multi-dimensional relationship between stress and strain defined in some more generic sense that characterizes the fully three-dimensional deformed state of material. In fact, it turns out that the definition of strain can actually be related back to kind of a gradient quantity of the displacement field itself. So also in direct analog, we have basically the stress depends on some kind of set of material parameters multiplied by effectively the gradient of the displacement. Ultimately, we can consolidate all these things down, and we can express all of these different equations directly in terms of some primary solution field of interest. In the case of mass transport, it's always possible to reduce these systems down into equivalent equations expressible just in terms of mass density. In the case of equilibrium and summation of forces, we can express everything in terms of effectively displacements as the primary variable that we're interested in. In heat transfer, it's temperature. And we could think of things happening in this sort of transient sense where there's a dependence on time. And in fact, we wanted to include dynamic behavior of, how does this chunk of material speed up or slow down or vibrate under kind of imposed loading conditions. We can include this extra term here. But it so happens it's particularly convenient, at least in our initial investigations, to just say, well, let's just assume things are at steady state. Things aren't moving around. Things have kind of settled down into their relative equilibrium states such that there is no relative change in density with respect to time. Things have kind of equilibrated already. Similarly, if we say, this object is at rest or it's moving at constant velocity, then we can say, well, this term, basically the acceleration, is equal to zero. And we can just say, well, static equilibrium then is just equivalent to saying this expression has to be equal to zero. And that makes things a little bit easier. So whenever I'm talking about steady state equations, really what I mean is the transient component or the component of these equations that depends on those partial derivatives with respect to time, just set that thing equal to zero. And that's where we're going to be concentrating a lot of our attention in this class, is on precisely these kind of static equilibrium kinds of problems. And the last thing that I'll kind of leave you with today is this conclusion, that basically I could look at things in this multidimensional sense. I could look at it, these kind of nasty looking equations that involve divergence operators and stresses and all these things and complicated tensor relationships between stresses and strain tensors and all that. But at the end of the day, we can kind of take a simplified, almost one-dimensional perspective on all these things and basically recognize that if we do this, and if we kind of utilize Fick's law or Hooke's law or Fourier's law and plug all those things into these equations and consider only steady state conditions, what we get are a set of partial differential equations that all look basically the same. We have, under steady state conditions, they all have to be equal to zero. And they all involve maybe some kind of local source term. And also they involve some second partial derivative with respect to spatial position x, relating to some particular unknown solution field, either mass density, displacement, or temperature, and depending also on some material constants that tell us exactly how fast does mass get transported through the material, or how stiff is the material, expressed through Young's modulus, in fact. Or, what's the thermal conductivity of this material? And all these different equations, in spite of the fact that they describe totally different physical processes, nonetheless are equally representable using the same set of governing differential equations. And this is really, this is where I'll kind of like evangelize. This is what I'll call truly beautiful. I mean, the fact that physics can be expressed in this unified way is basically just
all these physical processes expressing conservation principles writ large can be expressed using precisely the same set of equations. So even though most of this class, we're going to be focused on this, we're going to be focused on mechanics and equilibrium under applied forces. In the back of your mind, I always want you to be thinking about this. Even though we can kind of apply all these concepts and do finite elements and apply them to analyzing structures and their, how they behave under applied forces, at the end of the day, these concepts are equally applicable to different fields of physics, and we could use them to solve somewhat generically posed differential equations. So that's kind of where I'll leave it today. If you have questions, certainly there's office hours. Any questions before we end it today? All right. Well, yeah, go ahead.
File that you uploaded is not this one.
Yes, I made a few edits, so I'll replace that one so that it's consistent, at least on Canvas. But yeah, thanks for pointing that out. All right. Unless there's any other questions, I think we'll end it there today. All right, I'll see you on Wednesday.